to thank the organizing committee and the VIT University for inviting me. So I will be sharing my presentation with you once it is visible to you, so just let me know. So is it visible?
Yes, ma'am, your screen is perfect.
Fine. So good morning, everyone. So today I am going to talk about the topic AI-based technique for handling defects in software products. So as all of we know that companies, for example, Samsung, LG, Motorola, and Nokia, they keep on generating software products. Now with the development of these software products, so by default, some defects, some errors or bugs, they keep on getting introduced in these software products, so which may hinder or which may, lead to reduce the quality of software products. So instead of generating a single software product, the companies have adopted software product line approach. Now this approach, it lets companies to generate mass production of the software products instead of single product development, with the reduced development cost as well as time and with enhanced quality of software products. Now before I proceed with the topic, so the very first thing is to understand that what is software product line. So basically, it's a set of software intensive systems which shares a common and managed set of features which fulfills the particular needs of a market segment. Now, there are benefits which are associated with software product line. For example, it promotes reusability. So reusability is an important aspect in the industrial domain because nobody wants to start making the product from the scratch. So it is of utmost importance. It improves the quality and the productivity of the software products. At the same time, it reduces the development cost as well as time to the market. Now, for example, if I talk about Microsoft, so Microsoft, it offers some well-known product lines. For example, Microsoft Office, Windows, Visual Studio, and Skype. Although we have many variability models that do exist, which handles the commonality and the variability of software product line. For example, decision models are there, orthogonal variability models are there, and then we have textual variability languages also, which we use for modeling the commonality and variability of software product line. So out of these variability models, feature model is one of the most popular variability model, which represents the commonality and the variability of software product line. So now let's talk about feature model first of all. So feature model, we can say that it is a hierarchical tree-like structure. So all of us know that what's a tree-like structure. So we have the root feature, and then we have the child feature, and then we have the parent and child relationship between a root and the other features. So it's a hierarchical tree-like structure which includes features and the relationships between these features. Now, what is a feature? So obviously a feature is going to be a property, or we may say that it is a characteristic which is of interest to a user, which is relevant to a user. For example, if I take an example of mobile phone, so call forwarding and call waiting. So we can say that these are the two basic features of a mobile model. So same, if we talk about, we take an example of a car. So a car is having a color feature which can be of multiple colors like black, white, red, and blue. So these black, white, and red and blue, they become the features of car model. So when we have these feature models with us, now when these feature models, they start growing or the development starts with the feature models, so it may inevitably introduces inaccurate feature relationships. So some, different kind of inaccurate feature relationships gets introduced in it. And then, just a moment. So when we are developing or we are growing feature models, so what happens basically? So the inaccurate combination of features, it gets introduced in the model. So when we have the inaccurate feature relationships inside the model, so what it will do? It is going to create defects in the models. So these defects, now the point is how these defects arise. So these defects arise due to the incorrect combination of features. And we take this inaccurate combination of features from multiple software products. Now, what is the agenda behind taking the features from different model, different features? Because we want to develop a new product. So the defect is basically an undesirable property of relationship, and it occurs if the product illustrated by feature model does not correspond to its SPL. So in layman language, I would say that a defect is when you are going to develop a product and the product is not going to meet its requirements. It means it is going to differentiate from its requirements. So it means then there is a defect in it because it is not up to the expectation. So that is a defect. Now, these defects can be called as errors, or we can call it as deficiencies also, we call it as, right? And then, for example, I'll make you to understand that how these defects created trouble in the software products. So let's understand one thing. For example, we have a product line with us. Now this product line is already having few defects in it. Now when we are going to derive some valid products from that defective product line, so what will happen? Those defects by default will get inherited into the new products. So that is going to create a trouble. So defects can be inherited in the products which are built from a defective product line model. So once we have the defects in the software products that we have just created, so what will happen? Obviously, it is going to reduce or diminish the quality of the models and the benefits of software product line. So the main agenda behind this is to maintain the quality of the models and to focus upon the reusability agenda in the industrial domain. Now, we have the defects in the software product line. So obviously, when we are manually inspecting those defects in large size model is a laborious task, or you can say it's a cumbersome task to find out the defects by ourselves. So therefore, it is of utmost importance to resolve defects so that we can support the concept of reusability in the industrial domain. Although several methods do exist to deal with these defects. For example, we have, for example, proposition logic or natural language have been used to deal with the defects. But there were few limitations which are associated with these methods. So today I am going to talk about the AI-based technique which is used to deal with defects in software products. So basically, if I talk about artificial intelligence, so in artificial intelligence, we have various techniques to represent the knowledge. So one of them is rule-based system. The other one is first-order logic. So in this technique that I'm going to speak today, I have used the combination of first-order logic and rule-based systems, which are AI techniques itself. Now I'll be moving to the next slide. Now, before I start explaining this AI technique, so let's understand the basic concept which are actually required to understand this entire method. So we have three types of feature model notations. So one is your basic feature model, the other one is the cardinality based feature model, and the next one is extended feature models. So I would be explaining these feature models one by one in the upcoming slides. Now let's start with the basic feature model. So as I told that a feature model, it's a hierarchical tree-like structure. Here we can see in this figure. So when I say it's a tree-like structure, so obviously we have some nodes and edges in the tree. So node represents a feature and that edge represents a relationship between the two features. So this basic feature model, it explains the basic relationship between the features. It represents the commonality and variability in software product line. So here I would like to give you an example. What is commonality and variability in the product lines? See, long time back, a Nokia had two products. One was Nokia 1100 and the other was Nokia N73. So Nokia 1100 mobile, it had that torch feature in it. It had calling feature in it, messaging feature in it, right? And then Nokia decided to build another feature, another model, that is Nokia N73. So what it will do, it is not going to start from the scratch. So what it will do, it is going to reuse the features of the existing model of 1100 mobile. So it is going to reuse the features and the product. So when Nokia N73 is going to reuse the products from the Nokia 1100, so there may be a chance of getting defects in it, because maybe there is an incorrect combination of the features, maybe there is an incorrect combination of the relationship. So because of that, defects can be inherited in Nokia N73. So call forwarding and call messaging, they are the same features that we have used from Nokia 1100. However, this Nokia N73 had additional features like camera was there. So this can be the variability. Variability means commonality is the call forwarding, messaging, calling. These are the common features which were inherited in the Nokia N73. But if I talk about variability, so variability means the additional features which we have just included in the new product. That is, we have included Wi-Fi, Bluetooth, we have included camera, and so on. So the main agenda is when we reuse the existing product, so there are chances that defects will also get inherited. So in this work, a technique has been discussed which is going to identify the defects in the early stage, and so that the developers can solve their defects and we can have defect-free valid software products. So I hope this is clear to all of you. Now, after that, the valid combination of features in feature models, it allows to derive a software product. Now, this is one type of feature model that we have. Now, the another type of feature model that we have is cardinality-based feature model. So when I say cardinality, so obviously the concept of that UML comes into the mind. So in cardinality-based feature model, so basic feature model is extended with UML like multiplicities, or you can say the cardinalities of the type min and max. Now min and max, they represent the lower and upper bound respectively. Now I'll be explaining this min and max concept with the help of this figure 2. So this figure 2 is an example of extended feature model. Fine. So this 1 and 3, keyboard is a feature. This keyboard is having child features as QWERTY and walk. Now this QWERTY and walk, they have the cardinality of 1 and 3, where 1 represents the min value and 3 represents the max value. Now the relationships introduced in this notation are feature cardinality and group cardinality. Now the third type of model that we have is extended feature model. So you might have heard about the attributes, you might have heard about the properties. So feature attributes are used to provide additional information regarding feature. Now I will be relating this theory with this figure itself. So here we can see that this QWERTY is a feature. Now this QWERTY is having attributes like development time 1000, development cost 50. So means these attributes, they are providing additional information about the QWERTY key, QWERTY feature. Similar way, this development time and cost, they are the attributes which are providing additional information about this dwarf feature. So that's all about the extended feature model. Now, once we have understood all the three types of models, now let's see how a feature model looks like and what are the features, what are the various types of relationships that we have. Now figure 3 represents a feature model of laptop system. So here we can see that laptop is the root feature, and then we have hardware and software as the child feature here. And then hardware further have features camera, screen, CPU, keyboard, USB port, and so on. Similar way, this software feature, it includes operating system and application as features. Now, before I explain this model, so I think we need to understand the types of relationship that is being used in this model. So this table, column 1 represents the notation, column 2 represents the description of the relationship, and column 3, it represents the example related to this model itself for our better understanding. Now notation. So here we can see that P stands for your parent feature, C stands for your child feature, and then this relationship. This particular notation is known as mandatory relationship. Now, child feature C must be included in all the valid products whenever its parent feature P is included. Now let's relate it with this particular example here. Now hardware is mandatory, this dark circle, so it means it's a mandatory feature. So hardware is mandatory to be included whenever this laptop feature is selected. Now similar is the case with this parent feature and child feature, and then we have a circle, but it is not dark in color. So this particular notation is known as optional feature. So optional feature, optional child feature C means it may or may not be included in the valid products which are related with the parent feature P. Now let's understand it with the help of this particular example in the model. So camera is an optional feature. It is optional to be included whenever hardware is included. Means we may or may not include it whenever hardware is selected. Now we have third type of relationship, that is P is the parent feature, C1 and C2 they are the child features, and these two features they are related with alternative relationship with the parent feature P. Now child features C1 and C2 they are in alternative relationship with the parent feature P. It means exactly one of the child features has to be included for developing any valid product whenever its parent feature P is included. Means out of C1 and C2, we can only choose one feature. We cannot go ahead with the two features in the single product. Now, let's see the example in the model. So software for laptop, it may include Linux and Windows. Here we can see that Linux and Windows, they are in alternative relationship with the parent feature operating system. It means only one can be chosen. We cannot go ahead with both in single product. And then we have another type of relationship, that is OR relationship. So P is the parent feature, C1 and C2. These child features C1 and C2, they are in OR relationship with the parent feature P. When one or more child features are included for developing any valid product whenever P is incorporated. It means we can choose C1 or C2, or we can choose both C1 and C2 together in a valid product. Now let's understand it with the help of this example itself. So here we have the application. So application is selected. Whenever application is selected, Skype, internet browser, or these both can be selected together. Now we have the concept of cross-tree constraints in this model. So that includes implication relationship and exclusion relationship. So here we have C1 and C2, and then we have the implication relationship between these two features. Now features C1 and C2, they are related with implication constraint. It represents that C2, this C2 should always be included in all the valid products with C1. Now we can see here this implication relationship between USB port and Linux. So here we have this implication relationship. It means USB port implies Linux. So whenever USB port is selected, so Linux has to be selected. And then we have the last type of relationship, that is exclusion relationship. So C1 and C2, they are the child features and they have the exclusion relationship between each other. Now these features are related with exclusion constraint. It means both the features cannot be included simultaneously in the same valid product. Only one can be chosen. We can't go ahead with the two features in the same valid product. So here we have this exclusion relationship between operating system and between application features. It means only one can be chosen in the same valid product. So these are the types of relations which are used for this feature model. Now, once we've understood that how we convert a case study or any scenario into a feature model. Now, what are the various types of defects in software products? So we have considered 4 types of defects. So column 1 represents the type of defect and column 2 represents the description of the type of defect. So let's start with the first one first. So P is the parent feature, C1 is the mandatory feature because we have the dark circle over it. So it's a mandatory feature and C2 is an optional feature. And then we have an implication relationship from C2 to C1. Now this particular kind of notation, it leads to redundancy defect. Now a relationship which is modeled in numerous ways leads to redundancy in feature model because C1 is a mandatory feature means it is going to be part of the valid product. But this implication means that whenever we are going to select C2, so C1 has to be a part again. So it means C1 is occurring twice. So this is a redundant case. Now let's have a look on the next type of defect. So we have P as a parent feature, C1 as the mandatory feature and C2 as an optional feature. And then we have this exclusion relationship between these two features. Now C1 being mandatory will be a part of your valid product, but exclusion does not allow us to have two products in the same product. So it means C2 is being defined, although it is defined in the model, but it is not going to be a part of your valid software product. So it means this C2 is a dead feature. And then we have another type of defect, that is false optional feature. P is the parent, C1 is the mandatory feature, C2 is the optional feature. So C1 is mandatory means it is going to be a part of the valid product. Now C1 implies C2. Means whenever C1 is selected, C2 will always be selected. But however, C2 is an optional feature, means we may or may not include it. But due to this implication, this is going to be a part of your valid product. So it means this C2 is not optional anymore. Now it has become false optional feature. So this is one kind of defect. Now the next one is inconsistency. So we might have heard about the conflicting information, the contradictory information. So let's understand it with the help of this notation. So P is the parent feature, C1 and C2. They are the child features, but we can see that these are mandatory features, means they are going to be the part of valid products. But due to this exclusion relationship here, they both cannot be the part of same valid product at the same time, means one has to be. So it means this is a contradiction. This is a conflict. So the contradictory information in the model is defined as an inconsistency. So it will hinder the derivation of valid products from the model. So that's all about the types of defects that have been considered in this work. Now, let's see what are the various cases of defects due to redundancy. So what I will be doing, I am going to tell you the various cases of defects due to redundancy, then dead feature, false optional feature, and so on. Now, the defects due to redundancy, they have been categorized into 6 cases based upon some properties. For example, case 1 includes the redundancy defects due to exclusion constraint and group cardinality. So here we can see that C1 and C2, they are the optional features and they are in alternative relationship with parent feature P, and they are excluded with exclusion relationship. So this type of notation is going to be under case 1. Now case 2, it includes the redundancy due to mandatory feature and implication. So we have this R3 to R7 feature cases under this category. And then case 3 includes the redundancy defects due to multiple implications. So here we have the parent feature P, C1, C2 and C3. They are the child features. And here we can see that the implication 1 and implication 2 means the defect redundancy is occurring due to the multiple implications in the case. Similar way, in case 4, redundancy defect is due to multiple exclusion. So here we can see in this particular notation, P is the parent feature, C1, C2, C3, they are the child features. And here we have multiple exclusions in this case. So this is going to be a case of redundancy. Similar way, in case 5, redundancy due to cyclic implications, and case 6 includes the redundancy due to transitive implications. Now let's move ahead with the various cases of defects due to dead feature. So the defects due to dead feature, they have been categorized into 4 cases. So let's start with the case 1. So case 1 includes the dead features due to the mutual exclusion between full mandatory feature and optional feature. So here we can have a look on this D.1. P is the parent, C1 and C2, they are the child feature. C1 is your full mandatory feature and C2 is your optional feature. And exclusion between full mandatory feature and optional feature will make this optional feature as a dead feature. So this is one of the case under the case 1. And then we have the case 2. So this case 2, it includes dead features due to implication and exclusion. Now please have a look on this D.9 case. So we have the parent feature P, then we have C1, then we have C2 and C3. So all these are the child features. Now here we can see we have this exclusion between C1 and C2 and implication is from C3 to C2. So this particular case where we have this implication and exclusion, so it leads to the dead features. So C2 and C3, they will become the dead features here. Now, in case 3, dead features due to implication and group cardinality. Case 4 includes the dead features which are due to the exclusion and group cardinality. Now let's go ahead with the next one. So we have the various cases of defects due to false optional feature. Till now we have understood the cases of redundancy and dead features. Now these are the various cases of defects due to false optional features. So defects due to false optional features have been divided or categorized into 4 cases. So case 1, it includes false optional features due to implication between full mandatory feature and optional feature. So here we can relate it with this F.1 case. So C1 and C2, they are the child features. C1 is the mandatory feature or full mandatory feature and C2 is the optional feature. And then we have the implication from full mandatory feature to optional feature, which will make this C2 as a false optional feature. And then we have case 2, which includes false optional features due to implication and exclusion. And then we have case 3, which includes false optional features due to implication and group cardinality. And then then case 4 includes the false optional features due to exclusion and group cardinality. The last type of defect that has been considered in this work is defects due to inconsistency. So the defects due to inconsistency has been categorized into 4 cases. So case 1, it includes inconsistency due to implication and exclusion simultaneously. Means C1 and C2, they are the full mandatory child features that we have. However, implication and exclusion, they exist at the same time with these features. So this complete notation is going to be an inconsistency. Now, case 2, it includes inconsistency due to mutual exclusion between mandatory features. So here C1 and C2, they are the mandatory feature. So this exclusion relationship between the mandatory features C1 and C2 will make this complete notation as an inconsistency. Means a conflicting information or a contradictory information. Now, case 3 includes the inconsistency due to implication and exclusion. And then case 4 includes inconsistency due to implication between alternative child features. Now, the cases for these defects have been explained. Now, let's understand these defects with the help of a running example. So the running example that I have just discussed was laptop system itself. So if we focus on the left hand side part of the tree, so this is a tree which is having the root node and the child nodes are there. So all these nodes are being called as features itself. So let's focus on the left hand side part of the tree. So how a redundancy defect occurs actually. So we can see that camera is an optional feature. Screen and high resolution, they are the mandatory feature. Means screen is going to be a part of your valid product. So whenever screen is selected, due to this implication relationship, camera will automatically be selected. So camera is appearing for the one time. Now, in this case, high resolution is the mandatory feature. So it is also going to be a part of your valid product, but it is having an implication relationship with camera. So it means when we are going to select this high resolution feature, so again camera will reappear for the second time. So it means camera is going to be a redundant feature. So this is the case of the redundancy. Now, if we look into the right hand side part of the tree over here, so software is the mandatory feature, operating system is the mandatory feature, application is the optional feature. Now, operating system being a mandatory feature means it is going to be a part of the valid product, but it excludes application feature. Exclusion means that these two features cannot be a part of valid software products at the same time. Means only one has to be selected. So operating system is going to be a part of your valid software product, and this application, although it is defined in the model, but it is never going to be a part of your valid software products. So that is an example of dead feature. Now I have given the basic concepts of the types of defects, the model, the notations, and the cases of the defects. Now, this particular framework, it is basically the AI-based technique which has been used to handle defects in software products. So basically, in artificial intelligence, we have many techniques like proposition logic is there, then first order logic, frames, rule-based systems, and so on are there for representing the knowledge. But in this AI technique, the concept of first order logic along with the rule-based system has been used to handle or to deal with the defects in software products. So this framework is divided into 3 stages here. So we have stage 1, we have stage 2, and then we have stage 3. So as can be seen from the stage 1, so it transforms the model, feature model, into a predicate-based feature model ontology. And then as a part of stage 2, development and applicability of first-order logic-based rules. And then as a part of stage 3, identification of defects with the causes and providing corrections. Now I will start explaining stage 1. So basically what happens, we have the models which are available online on software product line online tool repository. So this is the name of the repository from where we have taken the models. These models are being kept by the researchers itself and from the industry people on this repository, and it's free to access also. So the models are already available on this repository. So the models were taken from this repository, but these models are in SXFM format, which means simple XML format. Now, there is a tool which we call it as feature ID tool. Now, this feature ID tool has imported this model, which is in simple XML format. Now, once it has imported this model in feature ID tool, now it is automatically going to read and analyze the model. After analyzing the model, additional features, just a moment. Now, once feature ID has automatically imported this model in it, so it has read and analyzed this model. Now, additional features and cross-check constraints like implication and exclusion, they can be induced or injected in the model. Now, an XML parser has been developed. This parser has transformed this model, which was in simple XML format, into a predicate-based feature model ontology. I would repeat that an XML parser was developed, which has transformed the model into predicate-based feature model ontology itself. Now, once we have the ontology with us, so before I move ahead to the stage 2, so I would like to tell that what is an ontology. So ontology basically is used to identify and define the basic concepts of any domain and the relationships among those concepts. So ontology is being used to provide the formalization to the model. See, whenever we want to process a model, so the model should be in a formal language. It should be formalized. Then only we can perform some operations on the model. So ontology is used to provide the formalization to the feature model. So this has been converted into predicate-based feature model ontology. Now, stage 1 is over. We have the ontology with us. Now, in case of stage 2, first order logic was used to develop rules, and then these rules were applied on the generated feature model ontology here. After applying these rules on the generated ontology, as a part of stage 3, the defects have been identified along with their causes and with the corrections. Now, the main point that we should see here is the causes and corrections, they are given in a natural language, in English language only, so that the developers, they can understand the cause of the defects and they can understand the corrections so that they can resolve the defects at the early stage. And these defects should not be inherited in the software products further. So this was the working of the this framework. And then this is the methodology which has been followed in this work. So I've already explained how this what is the process behind this method. Now let's understand this method or approach, or we can say the AI technique, with the help of a case study. So what has been done? So I have taken the feature model of e-commerce system. So this model was taken from Splot repository itself. So as we can see, it's a tree-like structure here. So e-commerce system, it's the root feature. The rest, all other features, they are the child features or sub features, we can say. Now have a look on the left-hand side part of this tree. So this rule R.1 means this particular case, it represents the redundancy 1. This particular case, it represents the redundancy 2, and so on up to 70. As I told that we have the model with us, but that is in simple XML format. Now we need to convert that model into an ontology so that the model should be in a formalized way and we can do the operations on that model. Now these are the transforming patterns that were used to transform the feature model into predicate-based ontology. Now column 1 represents the name of the relationship. Column 2 represents that how this particular relationship looks like in feature ID tool. And then this is the feature model representation for our own understanding. And then column 4 represents the predicate based ontology representation. So I will just explain one or two type of relationship. So let's start with the first one. So the first relationship is optional. So when we draw or when we have this optional relationship in feature ID tool, so it looks like this. So we have this feature one with the optional feature over here. The same can be represented as a feature model for our own understanding, and then this particular thing has been converted into a predicate. So this F, it represents the relationship where this feature 1, comma O, they are basically the objects. So what is the meaning of this predicate? Feature 1 is a feature which is optional. O stands for optional. Now, let's see the another type of relationship, that is mandatory. So this is how the mandatory relationship looks like in feature ID tool. And this is for our own understanding. Now, this particular notation or representation has been converted into the predicate. Now, this F represents the relationship. And feature 1 and M, again, they are the objects. So how I'm going to interpret it as feature 1 is a feature which is mandatory. So similar way, all the patterns have been created for the parent feature, exclusion relationship, implication, group cardinality, and or relationship. Now we have, once we have the model, we have that XML parser with us. So that XML parser has converted or transformed that model into the ontology. So this is the ontology which has been generated or created after the transformation. And this ontology was created using the patterns that I have just discussed in the previous slide. So this is the feature model ontology of e-commerce system model, because we are considering this e-commerce system model as a running example to understand this method. These are the first order logic rules. We can see that there are 17 rules in total, which were developed for redundancy basically. So these were the rules which were developed using first order logic, and these rules after the development was applied on the generated ontology. So once the rules were applied on the generated ontology, so these are the results that we have obtained. So here we can see this will give us the identified defect. What is the cause and what is the correction? For example, the defect is redundancy 1. So means redundancy 1 is a defect. And what is the cause behind this? Exclusion relationship between alternative child features A2 and A3 is redundant. And what is the correction? Eliminate exclusion 1. Now we can see that the cause and correction, they are given in natural language, English language itself. So it is very easy for anyone, or we can say the developer, to understand it. And accordingly, developer can take action to resolve these defects. So as to attain defect-free valid software products from the product line. So these are the results which were attained after implementing rules to e-commerce system 1 ontology. Now, as a part of any work, we have to discuss about the experiments and the results that we have attained. So let's start with the first parameter, that is accuracy only. So accuracy of the identification of defects, their causes and correction. So accuracy is equal to the number of identified defects with their causes and corrections divided by the total number of defects with their causes and corrections in model. And the results said that the proposed technique, it identified 100% of the defects with the causes and corrections in all models. Now, the next parameter was computational scalability. So we need to check out that is this technique scalable also? So this figure, it represents the execution time which was taken by all the rules per number of features to deal with all defects. So here in this graph, x-axis represents the number of features, y-axis represents the time in seconds. So if I talk about the first model, so it means this model, it includes 5,000 features. And when we applied the set of rules on this model to identify the defect, so these rules took approximately 0.510 seconds to identify the defects along with their causes and corrections. Similar way, the experiment was performed with a model with 10,000 features, with 15,000 features, and 20,000 and 25,000 and 30,000 features in it. Now, from the result, it was observed that the queries take reasonable time of 0.551 second to deal with defects in large size models up to 30,000 features. Now, the next parameter is number of features and costly constraints. So as I already mentioned, costly constraints include implication and exclusion relationship. So this figure 14, it represents execution time which was taken by all the rules in the models. Now the models are taken in different combinations. For example, figure A represents the models with different number of features. Here the models are considered with different number of implication relationship. Here in C, the models are considered with different number of exclusions, and D represents the model with different number of implications and exclusion, but they are in 1:1 ratio. Now from this graph, the results conclude that as an overall trend, the sky blue color line, this represents the mandatory features. So mandatory features, they improve performance, whereas mandatory and optional features which are in 1:1 ratio, they deteriorated in all the cases. So this sky blue color line, this is for the mandatory features, and this purple color line, this is for mandatory and optional features which are in 1:1 ratio. And from the graphs, we can see that it takes a lot of time for the identification of the defects. The next parameter that was considered for this work is height of the tree. So height of the tree means the levels that we are going to have in the tree. So it means, for example, if I say this figure 15, it represents the models with different combinations. Here A represents the models with different number of features like mandatory or optional. B represents a model with different number of implications. C represents a model with different number of exclusions. And D represents a model with different number of implication and exclusion 1:1 proportion. Now let's understand what is height of tree. So execution time of all rules as per the height of the tree with increasing levels 10, 20, 30, 40 and 50. This 10 means that they have level 0, level 1 up to 10. Then 20 means the tree is having 20 levels inside it. 30 means 30 levels are present in the tree, but this is the height of the tree. But these models were with the features 1000, 2000, 3000, 4000 and 5000. Now, from these experiments or the results, it is concluded that as an overall trend, this mandatory feature, the sky blue color line or the aqua color line, this represents the mandatory features. So the mandatory features, they improved performance as an overall trend. Now the next parameter that is considered for this work is number of alternative and or relationships in feature model. So this figure 16, it represents a model again with a combination of different number of features, different number of implications, number of exclusions and different number of implication and exclusion in 1:1 proportion. Now the execution time taken by all the rules with increasing alternative and or relationship in 1:1 proportion, that is 500, 1000, 1500, 2000, 2500 relationship. So these were the combinations of alternative and or relationships with features. Now the models with features 1000, 2000, 3000, 4000, 5000 were considered for these experiments. Now from the results, we conclude that as an overall trend, these mandatory features have improved performance. Now, once this AI-based technique, obviously by using this first order logic concept and the rule-based systems of AI has been developed and the experiments were being performed, so the results were compared with the existing work. It's an essential part of any research work. So as we can see here, I'll just be discussing one of the work. So for example, here in White et al., they have considered the model with 5000 features, but they have only identified inconsistency defect. And the time taken by their approach was 50 seconds. And in the same scenario, the AI-based technique, which has been discussed just now, it took 0.114 seconds to identify the same set of inconsistency defects. Now here we can see that this technique has been compared with the rest of the works. And then I would just be giving the description of the technique that is being discussed here. So the model included 30,000 features, redundancy, dead feature, false optional feature, and inconsistency. So these are the defects that were being considered and that were being handled by this technique. And overall 75 rules were created to identify the defects along with the causes and correction. 17 rules for the redundancy, 20 for the dead features, 17 for false optional, and 12 for the inconsistency. And these were the execution times which were taken by different set of rules for a particular type of defect. When we combinedly executed all the rules to identify all types of defects, so it took 0.551 second of time to identify the defects along with their causes. And now the last slide for the PPT is the conclusion. So after applying or creating this AI technique, so what are the conclusions that have been observed? The very first step is the model, feature model. It is being formalized, converted into a formal language on which we can perform the operations. So formalization of the model, it formalized the feature model from an ontological viewpoint by transforming it into a predicate-based feature model ontology. And after that, automatic identification of defects along with their causes and correction. So defects its causes and corrections were identified. Now, the causes and corrections, as we have seen, they have been identified in a natural language. So these are the causes and corrections. They are easily understandable by a product line developer. So that these causes and corrections, they can help developers to resolve the defects. Now, improve performance and scalability. The results indicated that the technique is effective, accurate, and scalable. It handled defects in large models up to 30,000 features in a reasonable time of 0.551 seconds. Now, the last thing is it improved the product line in terms of reusability and quality. It identified and resolved defects in the early development process model. It allows deriving defect-free valid software products from the product line by subsequently enhancing the reusability and quality of models in SPL. So I'll just come back to the industrial domain itself. So once we identify the defects in the early stage, so it means that if a company is going to create a new product, so it can reuse the software products which are there with the existing system. So that is the reason defects should be resolved as early as possible, so that these defects should not be inherited in the new products. So that's how it is going to be beneficial in the industrial domain. So these are the references that I have used for this work, and that's all about the topic.
Okay, so that was really a very unique and an interesting topic too. So participants, if you have any queries, you can please unmute and ask